Hi, and welcome to Trial by Air. I'm Ryan, and my co-host Rhythm and I are aerospace engineers. We want to share our knowledge and experiences in the field of aerospace engineering, but more importantly, we want to bring to you the knowledge and experience of experts in their field. We started Trial by Air to learn more about applied and theoretical engineering, and hopefully, when you come along with us, we can do a good enough job of explaining it so you can learn something too.
I'd like to welcome you all to today's episode, Catching Air. And today's episode is going to be a really fascinating and interesting one. Like aerospace, this subject is, pretty niche and detail-orientated, but, once you get to know a little bit more about it, it's actually a very, very, like I said before, fascinating subject. And so today with us, we have a NASA parachute engineer. And without further ado, let's just jump right in. So thanks for being on the podcast today with us.
Yep, my pleasure.
Okay, so kind of giving a broad overview of what's going to happen today is we're going to talk about parachutes predominantly and other recovery systems tangentially. So parachutes fall under the umbrella of recovery systems, which are used to arrest a vehicle's free fall to safely land it on the ground in most instances.
So kind of just jumping right in, and can you take us sort of through your educational history and sort of work history, kind of leading up to what you're doing today? Because I'm sure you didn't necessarily start with parachutes, right?
Pardon me. No, I did not. Went, of course, through school. Started with Lockheed way back in '88 or so, and got on with NASA, and pardon me. And eventually, I've done wind tunnel testing and a lot of other things, but mostly with parachutes in 1998. Started in simulation of parachutes, wind tunnel testing of parachutes, and designing of parachutes. So it's kind of been a long road, but kind of had all the background.
So I don't know if you can say, but can you give us some of an example of some of the projects you are able to say you worked on at your time at NASA or Lockheed?
I worked on a X-38, which was a parafoil program, and then got on to the Orion parachutes, and then after that got on to commercial crew parachutes.
Okay, so you have quite the pedigree. That's really impressive, and you've done that for, the past 32 years?
Since 1998, yep.
Since 1998,
Wow.
so 22. Yep. So
That's really cool.
All right, so kind of taking a step back, kind of looking at it from outer space, 10,000 feet up, as they say. What is the objective of a parachute? Just generally speaking, what does a parachute do in very broad and simple terms? What is a parachute designed to do?
It's a drag device.
Okay, so it generates drag to arrest the fall of an object, right?
Right.
That's the main objective in a very broad sense, right?
Yep, it's a drag device, plain and simple. Yep.
So I'm guessing the principal aerodynamics it relies on is the drag equation, right? Where you have drag is equal to, the dynamic pressure times the coefficient of drag, right?
Right.
And so I'm guessing you're balancing the dynamic pressure and the coefficient of drag in order to get what you want, correct?
You have to modulate the force.
Okay. All right. That's kind of your governing equations kind of right there, mostly drag generation and for a very high level, right?
Right.
Okay. I guess so. Knowing sort of like the main objective of it, I was wondering if you could sort of take us through like the preliminary steps of sort of designing a parachute, because I know, in my head I think of I just think of images, but I'm sure there's a lot more to it than just like simply just taking things that had been done before, and then just kind of like slapping it onto a new object and saying, okay, it's done and it's ready to go.
Right. So for speaking strictly for manned applications, not cargo, but manned applications, there are more than a few different types of parachutes. Usually you have a decelerator called a drogue that gets you down to manageable velocities, and then you will probably deploy another parachute that is a more gentle landing. And I'm not talking about paratroopers or anything like that. But for spacecraft that are 13,000 pounds plus, and they've gotten a whole lot heavier, 20,000 pounds, you have to have multiple parachute designs to get you on the ground. And there is a whole lot that goes into parachutes, starting with the textile. If you think of your common t-shirt in the weave, you pull it a certain direction and it's, kind of stiff. You pull another direction and it's not so stiff, and that's the way parachute textiles are. And it starts all the way from there. There's a few textile companies that what they call the broadcloth that is produced, and it goes all the way from there. Like I said, you look at your common t-shirt, look at how the seam is stitched, sewed, how close it is to the edge of the fabric. It's a lot more detailed than people probably ever thought of.
Kind of taking a little bit of a step back, you have to know what speed regimes your object is falling through, right? Because if it's let's say just a person jumping out of a plane, they're not going to normally break a supersonic or get near transonic in their descent, right? So your parachute is going to be different, or your, I guess, parachute recovery system is going to be different, right? I mean, if it's a spacecraft, it's coming in from orbit, so it's, pretty high supersonic by the time it enters the atmosphere and slows down a little bit. So that's a consideration, right? Just the different speed regimes you have to go through to get to, I guess, a manageable speed where you're comfortable with the occupants decelerating at, correct?
Right. And yes, you have to fall within certain human bounds that you don't want to pull like more than 3 Gs or something. And that's in different directions. So you have to take all those human factors into consideration.
So the human factors, so kind of, I guess, what was the hierarchy of design, I'm guessing? Do you start with the speed regimes? So these are the speed regimes that the spacecraft is going to fall through, or the object is going to fall through, and how do we arrest it? Or is the driving, I guess, capstone of the pyramid, of the design pyramid, the human, the occupant, or the payload, right? Is that what determines everything else? And for design considerations, that start at the very high level of what the human envelope is and then work on from there?
Right. You start with the loads.
Okay.
Then everything goes from there. You can only put so much load into the structure that's holding the parachute, and you only want to put so much whole load in the human. So it all starts from there.
So is that what differentiates between, like you mentioned, human, manned spacecrafts versus human-based parachutes, right, for paratroopers versus non-cargo or non-human cargo?
Right. Yeah, exactly.
Okay.
Probably not good to say this, but you throw cargo out of the back of the plane and you get 90% of it, you're good.
Okay.
But not so good for humans. But, if you're throwing out a bunch of pallets of water or something and you lose 10%, okay, that's okay. But,
right.
yeah, you're trying to modulate the load on the structure and the humans, more importantly.
And just kind of an interesting point, I'm guessing, is that since the parachute's under load, wouldn't that also be considered a structure? Because just thinking about this now, if the parachute's generating this a lot of drag, that's going to be transferred to the structure through those lines. So that's is that part of the structure, or is that completely just part of the analysis? Like, oh, we can only use these lines for whatever reason.
You don't want the parachute to fail what it's holding on to. In other words, you want the parachute to fail before the hardware fails. And I'm talking about where it connects to. But yes, the parachute is a structural grid. Of course, very flexible and very unpredictable. And you build in a whole bunch of margin. You've got to think about temperature, humidity, radiation, salt water, all kinds of things. And you have all these design factors where you have a whole bunch of margin.
Okay. I guess one of the other things that I tend to think of, it's a dynamic structure. So how do you deal with I mean, it's moving and falling, of course, and it's decelerating and there's forces acting on it. How do you deal with damping oscillations? Was that an issue in parachutes?
Yes.
Oscillations?
The higher the drag of a parachute, the more unstable it is. Unstable meaning what you just said was the oscillations, the pendulum motion, so to speak. And I think you can imagine that you have a high drag object and it's got all these wake interactions that cause it to bounce around. They call it a maypole, if you can, well, for your time, but a maypole going around a circle, or a pendulum. But of course you want high drag. But then again, if you have a low drag, like a drogue parachute, it's very stable because the air is flowing through it and disrupting all the vortices around that parachute. So it's very stable, but it's low drag. So there's a trade-off, and I don't know if I answered your question or not.
No, that's a good. I mean, it's kind of at least illustrating the point that this isn't. I mean, at least to my naive eye, it's like it's not just taking a napkin and taping some string and a quarter and saying, "Oh, it's just a piece of fabric, throw it into the wind." It's, it's very complex, and you have to balance a lot of benefits, pros and cons of each design or each way you want to solve the problem of decelerating someone to a reasonable speed where they can safely walk away.
Right.
Yeah, I wanted to ask. So you mentioned before you were talking about like failure modes, and I was going to ask, like, can you explain some of the different failure modes of parachutes? I'm sure they're not as simple as like, oh, there's a tear or it doesn't deploy, right?
Yeah, that's. I'm going to digress a little bit because that's something you just touched on about packing and everything. But going to your question. Yes, there are failure modes. There are joints and seams that you need to pay attention to. They have things in the fabric called rip stops, which is exactly what you would know the term is. It stops the rip if it was to propagate. So there's different elements inside of a parachute that are stronger than others, so a tear or whatever does not, like I said, propagate. The top of the parachute is called a vent, and that is one of the most important parts. If you picture a round parachute, there's a hole in it at the top, and that's the vent. And if a tear ever got up there and broke the vent, you'd lose the parachute. So that is typically one of the strongest elements and most paid attention to. Otherwise, there's other elements of a parachute that are definitely important, where suspension lines attached to what they call the skirt band. And those are paid attention to pretty closely. But the industry does what they call seam and joint testing, where the manufacturer will perform, like I said, go back to the T-shirt analogy, have a joint or a seam, and they will manufacture it and pull test it on a tensiometer and make sure the strength is within the margins. There are many details that folks aren't aware of, like a sewing machine. Your mom or your dad or whomever, made a dress or a shirt or something. There is a specific tension in the seam that they pull the thread through. And the needles have to be a certain sharpness. They can't be too dull, because every time you put a needle through a piece of textile, it damages it, which degrades the joint efficiency. So there's a lot of things. And then I'm getting way down on the details, unfortunately.
This is great because people don't know this, and they should.
And
yeah, I was going to say.
You have, again, I hate to keep going back to this, but my T-shirt analogy, there is an operator variability, meaning the person that sits down beside the sewing machine, maybe that person, did a really great job, and the next person, might have come in a little sick with a fever or something. And so you have those kinds of variability, and I'm answering your question in a long way.
I mean, it's good because it shows the detail and design. It's not just a piece of fabric that sits out in the wind. It's not a windsock.
Yeah.
Yeah, I was gonna say, I'm not gonna lie, I could not stop smiling during that entire conversation. It was really interesting to hear just sort of like the detail and sort of how important everything is when you like kind of walk through sort of parachute designing.
Yeah, I guess another question is the modes of failure. Another way. So, how can a parachute fail besides the fabric ripping? Of course, other ways it can fail besides. I mean, the two we kind of already touched is just not deploying or or just tearing itself to shreds. Is there another
right? Try not to get into the details, but the deployment itself is very chaotic, and the parachute can fold on itself during deployment, which would be very bad.
So, if I understand this correctly, if it gets tangled or the lines get tangled, or if it just doesn't unfold correctly, that would, based on what you said earlier, if you're turning this, the drag it's generating is going to change, and that's going to just change the entire environment or dynamics of the entire system, which could be catastrophic.
Right.
So can deployment, I guess that would lead to the idea that deployment can also induce oscillations right away, right?
Yeah. What we talk about is damping out the system. Mm-hmm. Depending on how long your parachute ride is, the capsule. Okay, so backing way up again, capsules as Apollo or what we have right now is below about Mach 0.6, they're unstable, which means dynamically unstable. And so the longer you're on a parachute, the better chance it has to reduce oscillations and its period. And where I'm going with all this is like a pad abort scenario. You're not on the parachutes that long, so you have to damp out pretty quickly to get your main parachutes out.
And that oscillation, I'm guessing, can also affect the inflation of the parachute, right? Because if the capsule is swinging, right, that's asymmetric flow around the capsule, right? If the air is moving more to the left or more to the right, and the parachute gets into that stream, that could affect inflation.
Right.
Or I guess another question, the kind of a two-prong question, is how do you control the inflation of a parachute? Because I'm assuming you just don't want to just uncontrollably send it out into the jet stream and let whatever speed it's at just, may succeed the design limitations, just shred it, which that's no good. It doesn't provide anything. And the second one is how do you control inflation? The first one's how do you control inflation? The second one is how do you deal with asymmetric inflation or asymmetric flow into the inflation of the parachutes?
Okay, so first of all, you guys are familiar with blunt body dynamics in airflow, so you've got a very bad wake. Usually the way parachute folks take care of this is called trailing distance. So you take a body diameter, and this is used in hydraulics as well. You go back 6+, depending on your Mach number. If you're supersonic, you go back 9+, like coming back from Mars or something. I'm sorry, you had controlling inflation. Number one, it starts with that. Controlling inflation starts really with packing. You're trying to deploy in a chaotic situation in the best uniform way you can. And that starts with orderly deployment. There's lines first, canopy first, but for manned space, the lines come out first and the canopy is last. After that, it's energy modulation, and they do that with what's called reefing. I don't know where that term came from, but you're constricting the skirt of the parachute to a certain diameter before what they call is fully open. So you constrict the skirt to minimize the load, and then as you're decelerating, you open up the skirt and finish your descent phase. If you think back to sky jumpers, they have what's called a slider, which is the same principle. If you've watched videos and everything, there's a piece of cloth that restricts the suspension line width until you've decelerated enough. But for round parachutes, it's basically the same.
Okay, so kind of getting on that idea of reefing. So we'll put an image of a slider working, so you don't have to verbally explain it for those of you who want to go watch it on YouTube with diagrams. I'd highly recommend it. But reefing, I guess you can imagine, is kind of looks like a jellyfish, right? Yep. Kind of moving a little bit, but except it's always expanding outwards, seeming to catch more air. I think you really succinctly answered those two about how do you control the asymmetric flow around a capsule, and like you said, like a pad abort scenario where there's a fire on the rocket and you have to get the crew out, and how do you deal with controlling that inflation at those speeds. So I guess we can move on and kind of really still kind of dive a little bit more into how parachutes are designed.
So I know that, like, for me, I've sometimes thought about, like, the advancement of computers, right? And sort of how far CFD has come, right? Through, being able to sort of successfully model airfoils and all that kind of stuff. And so I was wondering, like, can we do the same thing with parachutes? Can we, put them into computers and have those simulations be done? Or is it a lot more complicated than just simple, fluid mechanics?
Right. No, that's, I'm glad we're moving into the analysis area. For right now, and probably for me, foreseeable future, parachutes are highly empirical. You have to test them a lot, get a lot of statistics, good instrumentation, and model them that way. there is, you guys, even when I was going to school, there was something called fluid structures interaction. And I'm guessing that you guys had a little bit of that, which means that, being a flexible structure, the shape of that structure influences the flow, which in turn, the flow influences the shape. So it's a very difficult problem, and it's coming along. It's computational fluid dynamics, and there's quite a bit of research going on with that. But to answer your question more directly, parachute's highly empirical, and otherwise, you really can't predict them because of the chaotic nature.
Right. Okay. Ryan, do you have anything to add?
No, but I guess is that chaotic nature just due to the is it the necessarily the structure of the parachute? I mean, the flow you did say, but does the structure have more chaotic flow? Because I mean, you're getting supercomputers now that can model turbulent flow pretty well numerically, because no one, of course, has solved the entire Navier-Stokes equation not numerically, but mathematically, but computers, supercomputers can step toward turbulent solutions for Navier-Stokes very well. Is that the flow's problem, or is it kind of stuck in that interaction between the fabric or the fabric structure of the parachute and the flow?
What you just said, the last part, is that the shape influences the flow, but the flow influences the shape, right?
So it's paradoxical. It's
Yep.
chicken before the egg kind of issue.
They can do, I think they're getting pretty close with, a full open, steady state parachute, but it's the inflation portion and things like that. The very time dependent.
Oh yeah, that time dependence can really hurt a computer model.
But if you, way back when Rice University was doing steady state descent of full open parachutes, and I thought they were pretty good, but that's, certainly that's a big hill to climb, but that's not the end goal. The end goal is inflation.
Yeah, and inflation is the most chaotic part because of all the unfolding and stresses and loading of the fabric.
Yep.
Is there a way to do finite element analysis on the fabric loading?
There is. There's a couple of codes, but again, it's steady state, kind of fully inflated type things. It's not transient. There's a code that was developed way back in the 60s, maybe 70s, called CANO, CANO. And then there was another code that's called CALA, CALA, and I can't remember those acronyms at all. But what happens is you have the structural element of a parachute, pick out your favorite napkin, and you inform it with a pressure distribution, and you match that shape that you get from a photograph. So in other words, so you're in, grid gen, whatever, you apply a pressure distribution to get you a shape. You compare that shape to a photograph and say, okay, this is what we think we have. And then that code will tell you the stresses and tension and strains and whatever and all the elements that you put into it.
Is that for each individual thread on the fabric, or is that
No, it's down to what we would call the tape level. Like I'm trying to think of a good analogy, like your belt, a cloth belt.
a section of fabric,
Yeah.
like your sleeve of a shirt,
Yeah.
or piece of a component of a shirt, not
Right.
necessarily the.
But you go down to that level. You can coat it that finely, but you don't get down to like the thread stitch and all that kind of stuff. Stitch count.
Can they do that, or is that just not really necessary?
Yeah, you pretty much pound it with margin.
Okay.
So you mentioned that, parachuting, like not parachuting, but parachute testing is more or less at the moment empirical, and it might go along the lines of not CFD, but like computer analysis. So I was wondering if you could kind of like elaborate on sort of the different empirical testing that can be done. I know you touched on tensile testing, right? Kind of just like pulling on the fabrics and seeing how well they can withstand the structural load. Are there other tests that can be done?
Yeah, they, typically before you go into production or something, you'll have what's called a bench strip out test, which is exactly what it means. You put the parachute in the bag and you pull it relatively slowly, considering that when, like in spacecraft design, the main parachutes are pulled out at about 50 psf, and if you ask me what velocity that is, I'd have to go to a table, but it's more than 100 feet per second. But anyway, you do a bench strip out test, and then mostly you do testing, and it doesn't have to be high fidelity testing, meaning that you're pulling out of the actual bag, out of the actual compartment, and all this kind of thing. But you derive certain empirical constants from the test that help you inform your analysis for performance, and then you run those in Monte Carlos and get some kind of Gaussian distribution to where where your tails are on the inflation curve. So there's a lot of testing that goes on.
For the design of the parachute, is there any initial wind tunnel testing, or do they do subscale model drop testing?
No, I shouldn't say that so definitively, but in my opinion, subscale parachutes, it's not an extrapolation. It doesn't work very well. Wind tunnel testing does not work very well either, because the material stiffness does not translate to real life. So you can imagine, we're flying 104, 116 foot parachutes, and you put in, which I've done, you put in a small parachute, small being maybe 10 feet in diameter. The material properties do not scale, and just have not had a lot of luck with it.
Is there, I know in wind tunnel testing, they have variable densities for Reynolds numbers.
Mm-hmm.
Is there something similar in terms of parachutes, or just because of the way the fabric behaves, you can't have a dimensionless constant that replicates that, I guess, parity?
My opinion, to be mostly fabric, but fabric stiffness and fidelity. We, a vendor of ours, did a great job of laser cutting some very thin material. Is probably one of the most exact replicas of a parachute I've ever seen, and it did not perform worth a darn in a wind tunnel. It was not even close. Could be Reynolds number. Machine work. No offense to the people that manufactured them, but it just did not translate at all. So going back, I said that parachutes are highly empirical, and the few parachute vendors there are, you don't really try to, you go what's on tried and true. You don't try to reinvent the wheel. You just like, okay, this has worked in the past. It's going to work now. Let's go.
Right. I mean, you really don't get any do-overs.
Mm-mm.
There's no go around for final landing. This isn't,
Right.
So all parachute testing is at full scale. Is it necessarily the full system, or do you test system components and then, if you like you said, you have a drogue parachute, then that can pull out two other drogues or whatever. Is it? Do you do a full system test to get the whole interaction, or do you do individual components and then compile them to a system for a full drop test?
Usually, speaking from Orion experience, it was component testing. But in the end, and you guys will learn this, it's called qualification testing and certification. And qualification, as far as parachutes go, is a full up system test, meaning that they have what they call tests like you fly exceptions, and you document them and you rank them. It's not good or whatever, or it's close enough. But usually qualification for parachutes is you've got the proper four-body wake, which we've talked about, the capsule. You've got everything, except maybe instrumentation, because you're trying to take loads and whatnot. That would be a test like you fly exception, because we're not measuring loads on, the spacecraft. But yeah, qualification testing is a run for the record, and you're saying this is safe for human flight.
And then you said qualification, and then was there verification testing?
Certification.
Yeah. Certification is the human flight.
Yeah, that's you
rubber stamp it.
Yeah.
Put your name on the line.
Quite
yeah. Literally.
Dot your I's, cross your T's. Yep.
Okay, so I guess we have all these components we've talked about in testing, analysis, design. Let's talk about a deployment sequence. So what happens before a parachute? Let's talk about before the parachute deploys, before it's on the vehicle it's going to be deployed on. What happens to that parachute before it's deployed? Like packing, as you said. What does that entail? What is that process? What is the process before you put a parachute on a vehicle? I mean, from where it's manufactured, not necessarily from each stitch of cloth to stitching it together, but you have a parachute, let's say, it's all laid out. What happens before you put it in a vehicle? And it's already been tested.
It's painfully documented. I'm going to start from the ground up, and I'll try to keep it short. The vendor will receive the textile. They will sample the textile. They will pull test it. They will document it. Then it gets manufactured. The parachute does. And that goes through a whole bunch of quality type things. And then you literally, like you just said, pack it. You put it inside the bag, and this is assuming it's all been tested. You got your packing procedures down, everything. The vendor will pack it. They ship it to whomever, whether it be Orion or SpaceX or Boeing. And those personnel will integrate it into the vehicle with procedures, photographs, documentation, all kinds of things. And then it goes to the pad, and you guys have probably looked at pad abort videos and things like that. So
yeah, I guess another thing to kind of talk about it. So let's say we get to the point where it's in the deployment phases. What is the first thing that happens? Let's say the spacecraft has aerobraked enough. It's approaching whatever stability, like you said, blunt bodies usually Mach 0.6, correct? When they start to become dynamically unstable.
Yep.
What happens? What happens to get those parachutes or whatever part of the system out to get the final chutes out? What starts the process?
not going into software avionics, but pyros. Pyros eject your first parachutes out. They're called gas generators. And exactly what you think that means. It's a pyrotechnic device that launches something out of a tube. And that's the drogues for Apollo, CPAS, SpaceX, and Boeing.
And for just to kind of clarify, CPAS is the parachute.
Oh, I'm sorry.
Orion.
Yeah,
I mean,
CPAS is for Orion, right? Yep.
Yeah. So those drogues come out, and then depending, I guess, on the sequence, those drogues will be attached for some time, and then I guess we didn't really cover this, but there are line cutters that are used to between the phases, correct? And those line cutters are important.
Yep. That's we talked about reefing, and these are pyrotechnic devices that are fuse driven. They are mechanically operated, meaning you pull the pin, starts a fuse train, and that lights off a charge that will cut, depending on the rating and everything, will cut a line to, as we talked about, modulate the force.
Okay. And then, so the drogue stabilizes, and then the avionics tell the line cutter, okay, cut the drogue, and then the drogue will pull out the next.
For SpaceX, the drogue pulls out the main parachutes. That's called cargo delivery or cargo deployment, that is. And but for Boeing and Orion and Apollo, the drogue's cut away, and then there's what's called a pilot parachute that will deploy the main parachutes. And those pilot parachutes are mortar deployed.
So, not to get into the weeds, but a pilot parachute does what compared to a drogue parachute? What is the benefit of using a pilot over a drogue? Not kind of going to the design philosophy or choice of either contractor, but just kind of what does a pilot chute provide?
I wished I had a great answer for that. Pilot parachutes on the, so engineers will look at things from the reliability perspective. How reliable is a system. And during Apollo, and I never got this answer, why the pilot deploying the main parachutes is more reliable. But there were some, safety folks and statisticians and everything that did research and said it's better if you have a single parachute deploying each main parachute.
Okay. So I guess, that we pull out the drogue, and the drogue either pulls out the mains of the pilot, and the pilot then pulls out the mains.
Right.
The mains inflate, and then they reef to full inflation, and then the splashdown, hopefully everything's great. I guess one of the kind of interesting things I've noticed in splashdown videos is that I don't know if it's for technically parachute reasons, but the capsule's canted. Is that for airflow purposes?
It's for water penetration. So imagine yourself when you were a kid and you dove into a pool and did a belly flop, or I don't know, take your favorite piece of wood and you landed straight down. You have to have what they call a knife edge to break the water surface tension.
So you can decelerate slowly as opposed to very quickly when you hit the water flat.
Yeah, you want to kind of, you want a knife edge into the water because, like I said, the surface tension causes a lot of loads. And so you kind of cut yourself through the water.
So after the
and plus the structures folks build the capsule a certain way to take those types of loads. There is a range of angles and rates that the structures folks will design within And so that's, another reason for when we talked earlier about the oscillatory nature of parachutes.
I guess, okay, so the capsule landed and everything's fine, the parachute's inflated. What happens after the capsule lands and the parachutes come down or deflate essentially because there's no more air moving through it? What happens then?
Usually, spacecraft have a cutaway for the parachutes because the wave action will actually sink the parachute, and the parachute could pull down the spacecraft into the water. So they usually cut it away. And one thing that gets lost, and this is way down in the detail, parachutes are data. So you want to recover them because you want to look at, well, were there any rips? Is, something unexpected happened that we didn't know about? Because the hardware is always talking to you. So usually try to recover them as best you can. Not always possible, as you guys probably saw in the video a year or so ago. There was some fishermen that found some spacecraft parachutes. But yeah, always try to recover them.
Yeah, go ahead, Rhythm. Sorry.
I was going to ask, speaking of recovery, do you guys ever, or rather, is it possible to reuse used parachutes, or is that more of like a taboo against, like, not, we shouldn't do that?
I will say there is a vendor of ours that has a 5 use goal. SRB parachutes from the shuttle world, those were reused. Of course, that's cargo, it's not manned. But KSC, Kennedy Space Center, had a big refurbishment facility where they washed them, dried them, and reused them. So it's not unheard of.
For manned flight, is there any parachute reuse?
There is a goal for that, yeah.
Okay, but it hasn't happened.
Not yet, no.
Okay. Mm-hmm. And even with the Russian Soyuz capsules?
I don't know much about that.
Yeah, okay. No, that's really cool. And then I wanted to ask, how hands-on have you been with, like, parachute testing yourself? I mean, kind of going back towards testing here, but, are there any cool experiences that you've had with, like, parachute testing that that have stuck with you to this day?
Oh, yeah. I'm wondering what I can talk about. Usually, there was a well-known person from one of our vendors that said, "You're not a real parachute engineer until you've destroyed one." And yeah, they're spent a lot of time out in the desert testing parachutes, and time in the wind tunnels as well. But no really, close calls or anything. I mean, I saw one parachute fail, and the test vehicle pretty much went supersonic into the ground. One of my first tests. Yeah, it's not for the faint of heart.
I guess on top of that testing point, you said you designed parachutes at one point. Have you designed any parachutes that you tested, or have you been involved in any process like packing or, dropping your own parachute design?
I've bought parachutes off the shelf that I've had modified and wind tunnel tested and flown. For a while, I was probably the sole person at JSC that deployed a parachute at better than Mach 0.6, which, of course, manned space, you're not going to be doing that much. But to say that I designed it is not correct.
How involved were you in that process of that parachute that deployed above Mach .6?
I was it.
You did the whole thing.
Yep.
You packed it.
Yep.
How long does packing usually take? Or I guess how long did it take you when you did it?
Depends. The packing process is, it's pressure packed because you're trying to save volume and everything for a spacecraft, right? And like a drogue parachute, which is 26 and a half feet. The vendor got really good and could pack one in about 3.5 days. And that's, you go home, you let it sit overnight, things like that. It's not a 24-hour process, so to speak, not like you're a doctor and at a hospital and everything. But, and the bigger parachutes are about a week. But you put in a couple of layers, you press it to a certain force, and you let it sit. They call it a soak. And then you release the pressure and put in some more fabric and then do it all over again. And then there's different compartments and everything. But yeah, main parachute's about a week, 5 days or so. They can compress it, but compress the timeline. But, but yeah, it's a time-intensive process for a couple of seconds of nail biting.
Is there like a specific folding pattern that you have to like follow, or is it just like? I'm sure there's a specific folding pattern, but is it like a very rigorous sort of folding pattern, or can you kind of do different types of folding patterns to get it?
No, there should be no artistic license. The procedure is supposed to be written as such in photographs and whatever, that anybody with knowledge of parachute rigging and packing, that they can come off the street and pick it up and make it repeatable. That's the whole thing about parachutes. You want them to be repeatable as best you can. You're trying to control chaos. So you want things rigorous. What we typically follow is what procedure-wise is what we call red lines, which means you start out with the procedure, you've done it in your labs, and you're like, I didn't do this step correctly, and let me modify it. And so that's a red line. And what you want to see is stability in the procedures where there's minimal red lines. So I cannot tell you, tried to explain to folks that, a term we use is touch labor. People are physically touching it. It's not a CNC machine, right? You've got hands on it. You got your fingerprints on it. And people, let's say the vendor is trying to accelerate the pack process. So, we talked about sewing machines. So you've got one person that's got, halfway through the procedure, and then the second shift comes in and they got to take up where the other guys left off. And it's just because of human nature, it's very imprecise. And that's what you're trying to control.
It sounds like, like all things parachute, it sounds like it surrounds the idea of just like stability, right? Ranging from procedure all the way to deployment. Yeah. And like you said, I think it was a good example, or it was a good way of saying it. It's like controlled chaos. You're trying to control chaos.
Yep.
Yeah. I guess we have two more questions, and then we'll thank you for your time. I guess three maybe. How big is the parachute community? How big is the recovery systems community? I don't know, but you mentioned vendors, and I don't know how big is that community of engineers and managers and manufacturers? Is it, sizable like a commercial aircraft company where it's multinational and spans across the country, or is it relatively niche where it's one or two companies and organizations that control the whole thing?
As far as manned space goes, and probably military for that matter, I'm not talking about recreational jumpers. It's very small. Everybody pretty much knows everybody. England has, I don't want to call it big, but there's a lot of parachute folks in England. I've worked with more than a few of them. ESA, European Space Agency, they have a few, but over here it was called Irvine. Now it's called Airborne, and they're out of England, but they're a very big contingent. Pioneer, it's called Zodiac, and now I can't remember who in the heck they're called right now. They get sold a lot. They're a French company. Well, Pioneer was American, and then Zodiac, which is French, and then I can't remember who they're owned right now, but they're big in the planetary stuff, and they're kind of moving out of that actually. Not their desire, but the company that owns them desire. But yeah, it's a very small community.
What government organizations are involved? You mentioned ESA. Who else besides NASA and ESA?
I can't think of any.
DoD.
Well, DoD because of the paratrooper element, but yeah. I mean, manned space is pretty small, so.
Yeah. And no, like JAXA or the Indian Space Research.
JPL. I mean, because they do interplanetary stuff, I suppose. But yeah, JPL, their Mars things.
I guess one more question to ask is, if people are interested in this, parachutes and recovery system design, what resources can they look to for education? Because this isn't something that's, at least from Rhythm and I's experience, offered in college at all. I mean, it's not even elective as parachute design. So what books or resources do people have that are available for them to learn more about this?
There's Knacke, which is the handbook that, as old timers have called it, from the 40s. It's a basic primer, and other than that, pretty much AIAA type papers. Like you said, it's a small community, and it's a niche, and it's fun, it's exciting, but it's not everybody's cup of tea.
Yeah, so the book is called Parachute Recovery System Design Manual, T.W. Knacke. It's German, I believe. We will put links in the description for anyone else, along with databases, at least the US-based databases for aerospace research, like NTRS, National Technical Report Server, AIAA's their report server, and the Defense Department's DTIC report server. So you can access that if you're in the US. Don't really know anything else outside of that in terms of European or other country based, but yeah. All right, Rhythm, you want to ask the last question?
Yeah, I guess, to kind of close this off, is there anything else you kind of wanted to share with us that we didn't get to, quite talk about yet, or not yet, but didn't get to, kind of cover? Something that you kind of want to, leave the viewers with as like sort of like a closing remark?
Not really. Just, I can't emphasize enough how chaotic parachute deployments are. You do your best to pack them to where they come out orderly. You're in a dirty 4-body wake. It's, of course, me being this close to it, I certainly didn't understand the difficulty of it. So, yeah, it's not as straightforward as people like to think.
Yeah, it definitely doesn't sound like that, but it also very, I mean, going into the detail, it sounds extremely interesting, and, it just goes to show how detailed aerospace engineering really, ends up being.
I want to take this time to remind everybody that the views expressed by the host and their guests are theirs alone and do not represent the views or positions of any government agency, academic institution, or business that is associated with the host or their guest. If you like this content and want more, be sure to check out our Trial by Air podcast, where me and my co-host Rhythm discuss aerospace engineering and aerospace engineering related subjects, sometimes with the help of a special guest. We post a podcast episode every Sunday. Thanks for watching.